Okay, hi everybody. Welcome to the last exam. You're left with one more exam. I hope you had a good exam season. I missed you guys a lot. I missed you guys a lot. Now one more exam, and you guys are done. Semester one is over. Let's just try to quickly. Let's just try to quickly go through questions. I'm going to be going through questions with you, and we see how it goes. Okay. If you have any question, you send it to me on WhatsApp, and then I'll also have a look at it and see how it's going to go. We just want to try and prepare as much as we can for tomorrow's test. It's a walk in the park. It's not even hard. We just want to make sure that you do the right things when you're in the test, and then you quickly get the calculations. You leave, and you have a very, 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 very good holiday. Okay, let me share my screen. Let me share my screen. Give me a second. Right. Can you see my screen? I think you can. Okay, I can see it. Okay, good. So here's the test. I want us to look specifically at chapter B. You prepare yourself for section B, part B, and you try to be as ready as you can. This is the something that I'm just doing to make sure you are all ready and you all do well. So here is, let me zoom in. Let me zoom in. Sorry, the quality is bad, but here's the thing. You've got multiple choice questions. We'll see. We'll try to look for as many multiple choice questions as we can and talk about them. But look at part B. Yeah, you have 3 multi-part questions. So you're going to do 3 questions, and one is going to be graphs. The other one is going to be momentum. Then the other one is going to be something to do with the free body diagram. So one is going to be graphs. The other one is momentum. The other one is free body diagram. Give me a sec. Give me a second. Sorry. Okay, so remember, what I want to quickly show you. Sorry, I'm back. What I want to quickly show you is how to do the question for each type. Okay, so we'll start, obviously we'll start with those that you do free body diagram. Then we're going to do those that you're going to be doing for the collisions, how you draw diagrams also, because for those ones you're going to go to draw what we call system diagrams. So you're still going to draw diagrams there as well. And then we'll see also for graphs how you quickly do the things. So if we can go through, a lot of the questions where you'll be drawing free body diagrams, you start meeting them at chapter 8 and 9 and 10. And what we are going to be really focusing on is free body diagram, and here, where we are going to resolve forces and try to find acceleration using that. That is where we are focusing on, because that is the question that is coming. Okay? Forces when a body is accelerating. So you're just going to draw your free body diagram, and then you're trying to resolve for forces where you're going to have it not in equilibrium. So that is the situation where we want, where you have something that is moving. That is what we're focusing on. And also we're going to have for collisions, then we're going to, so don't waste your time thinking about a situation where you have something that is not moving. Don't waste your time. 9 times out of 10, the situation which you have is either going to be a spring or a pulley. I'm predicting this one. where you have a body accelerating or something falling in the sky, but it's not going to be something sitting on the table or whatever, where you are going to have the sum of forces being zero, or something that is just on a trampoline or whatever. It's out. We're not going to do that one. We're going to do where things are, you have compressed a spring and you have now released it like a box. Or those are the type of questions we are looking for right now. And we're going to be drawing the free body diagram, and we're going to be resolving, knowing that there is an acceleration. And then when we feel like we're ready with those ones, we start to look at those that have to do with collisions and what we should just make sure we do. Those are simple. Momentum is a walk in the park. Momentum is like, obvious stuff. Then from there, we just see the graphs and how to do those ones. Okay? The things that you should do and remember on graphs. So let me go back. Let me go to questions. I'm going to do this. I'll be just looking for questions and doing them with you quick, fast, trying to do hopefully we can do a question that is like the one that is coming tomorrow, or we can do the question that is coming tomorrow. Okay? So let's see. I'm going to go to ASAP. Look at this one. I'll be just doing questions, but I'm focusing on the questions that are coming. Only, okay? We'll do multiple choice. I'm focusing only on the questions that are coming. So you say to me, are we going to do this type of question? This type of question, which is in B, where they say a book is balanced? No. This one is out. This one is not coming tomorrow. It is out. Why is this question out? Because of this statement. A book is balanced. The fact that it is balanced, that means there is what? There is no acceleration. Now we are doing ones where there is acceleration, because they said in part 3 there is going to be acceleration, although it's a very, very similar way of solving. Although these things have a very similar way. So I mean, if you go through your slides and you go through the questions, you see that if you go to, let's say, 8 part 1 and 8 part 2, especially 8 part 2 and a little bit of 8 part 1, it is about these things which you're going to see, these type of diagrams like figure 6. So let's say you struggle with pulleys. If you want to understand pulleys, you go to 8 part 1 and 8 part 2 in tutorials. That is where they deal with pulleys. And what you are going to see is that when you are dealing with pulleys, when you're drawing your free body diagrams, of course you're going to draw your boxes individually. So you're going to draw your boxes individually, and in here there will be the name of a tension, and you put it this way, and in this same rope, a pulley is one way. It just makes sure that the same rope is going to be applying the same force on 2 different objects, although the force will be in different directions. That is what a pulley does. It makes sure, like if you see this box here is being pulled to the right, and this one is going to be pulled up, the force is exactly the same. So what we want to find out is there going to be acceleration in this situation for number 3A? If there's going to be acceleration, then we are going to solve it, because it is representing a type of problem that may come tomorrow. Here they're saying, blah, 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 blah. I'm not going to read. Frictionless table. If it's frictionless table, that means for horizontal forces, because horizontal forces, we could have had friction and the tension in the rope. But because we don't have friction, that means the only horizontal force that this thing is experiencing is going to be tension T, which is going to be like this. And in here, of course, there's going to be, we can put it going down like this as the weight, okay, which is negative of, you can put it, because it's facing down, negative of 2.00 kgs times 9.8. But does it matter, this one? No, it doesn't matter. Why doesn't it matter? Because we don't care about up and down. We do not care about up and down right now. Like, this thing is on a table, so obviously it won't go up and down. We're looking at horizontal. So horizontal, since there's only one force, of course there is going to be some acceleration. Now let's go and find out what they say. Also assume blah 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 blah, frictionless pulley, blah blah blah. I actually don't read. And therefore both blocks experience the same acceleration. Okay, so both blocks experience the same acceleration. Yes. Now they said if air resistance and any other friction are ignored, and any other friction forces are ignored, what is the magnitude of the acceleration of this 2 kg block? Which one is this? Looks like it's 1.00 kgs. Then this one is 2.00 kgs. So here they're saying they want the acceleration. So they want acceleration of body number 2. Anyway, if you want acceleration of body number 2, these things have the same acceleration. But if I'm looking at the 2 kg thing and I want to do anything to do with the calculation of acceleration depends on forces. And if you're dealing with anything to do with forces, you need the free body diagram of that thing. So here they are talking about the what? 2 kg block. Do you have the free body diagram of him yet? No. Go ahead and draw him. So you draw the free body diagram of the block. And when you are drawing free body diagrams, don't look at objects to say, oh, there is a table, oh, there is a pulley, oh, there is a crane, oh, there is this. No. Just look at the object itself and you represent it with a dot. And look at the forces that are acting. Don't worry about the shape. So in here we know that this force has a weight, which is the weight facing down. Weight object number 2. Then we know that it has a normal force, so there's going to be normal force of object number 2. But we do know that it has a force here, which we'll call tension. And we can call it tension in rope 2-1, whatever. Tension in rope 2-1. Now, this is going to be very interesting because these are the forces. There is no friction, so there is no other horizontal force. Now, this is for object. This is for 2 kg object. Now, for the 1 kg object, let's put for 1 kg object. What do we have? For 1 kg object, what do we have? We're going to have its weight. Weight is equal to negative mg. Then we're going to have what? The tension. Tension by 2 in 1. Okay? If you go and look at it here, you see that's what happened. There is the weight, then there is the tension. So this is what is going on. So what you must know is that from here, we start by resolving for 1 kg object. You're going to say the summation of forces in the y is equal to 0. Here it is not equal to 0 because there is some form of acceleration. And that acceleration, do we know it? No. We'll say ma. We'll call it ma. The summation of forces in the y will be equal to ma. Now, what is it going to be, the summation? Because it's not equal to 0. They say that these things have accelerations. So their resultant force is equal to ma. Once you are told there's acceleration, that means your resultant force is not 0, it is equal to ma. That's the situation you are doing tomorrow. You're not doing resultant force equal to 0. So we actually know that they're not the same. So here what do we have? We're going to have tension 2-1. Then we say minus W. This is equal to ma, which is going to be, let's put tension 2-1. Okay, it's actually plus. Resultant force you always add. So we say plus. What is the W? W is negative of mg. This is equal to ma. And what you end up having is going to be T21 minus mg being equal to ma. Right, this is what we'll be having. Remember what they want us to find is what? What they want us to find is going to be the acceleration. We want to find what is that acceleration? In here, this acceleration. And what do we know? This acceleration is going to be the same in here as well. So now what we are going to say, this is the tension 2-1. You'd say the summation of forces in the x is also equal to ma. Okay? The summation of forces in the x is equal to ma. Now, what is the summation of force in the x? You have tension 2-1. This is equal to ma. Now, what is your m? In here, the m is 2 kgs. In there, the m is 1 kg. So what you're going to say is, you're going to say here, tension, sorry. In here, you're going to say, you can make whoever you want the subject, okay? You can say tension 2-1 minus mg. What is mg? 1.00 kilogram times 9.81 newtons per kg. Then we say this is equal to 1.00 kg times A. So you can now say this is going to be equal to T, what we have? We have T21 minus local. So you can see this. What would you have here? 1 kg, T21 minus. Here you have 1 kg times 9.81. You have 9.81 newtons. This is going to be equal to 1 kg times A, that is A. Now we take that A, we go and put it here. We're going to now have T21 is equal to m multiplying, what is it now multiplying? It is multiplying T21 minus 9.81. That is the A. We got it from here, and because they told us the acceleration is the same, so that is why we are replacing it. Now what are we going to have? T21 minus m by T21 minus m by 9.81. Now we're going to put T21, okay? Do we say it is equal to, sorry, it is equal to m T21 minus, here you're going to say T21. So what do you get? T21 minus, or we can take it to the other side and we have here m by 9.8 is equal to m. So in here what we'll end up getting is we're going to end up getting m times 9.8. We can take it to the, we want to find T21, so we can say m by 9.8 is equal to T21 by m. So it becomes m by 9.8. So you'd be saying here, what is the m? This m here is going to be this one, which is 2 kgs. So you should have said m2 or something. 2 kgs, then what we will end up having is this is going to be equal to and we can say that this will be equal to since we factored out T21 here, we would have remained with m minus 1, and we would come and bring that m minus 1 to say m minus 1. And it would be 2.0 so in here what would it be? 2.00 kgs by 9.8 what would it be? 2.00 so what do we get? Here we just remain with T21. Yeah, it's only T21 because this one, it is m minus 1 has gone. So what do you mean? So look here, you can punch in the calculator, then you get your thing. So let's put, what is it going to be? Two times 9.8 divided by 1. You get 19.6. And what did the question want? They said, okay, we found T21, but we need acceleration. They want acceleration. So in here, here you can have this, you can put it in here. T2 is MA, so you can say T21 is equal to MA. So what is it going to be? So if we say here 19.6 minus this 2.00 kgs, what do you get? Here we got it, and 9.8 is equal to P. Okay? So, yes. So, we got our acceleration. Yeah. Okay. That's what you do with this one. Next one. Trajectory of the ball, blah, 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 blah. We'll do it. Here is one for collisions. But you can see in this one, the section head, this book one, which you're not going to do, because it's balanced, then we have this one again for success. So, yeah. Give me 1 sec. Give me 1 sec. Right. That was one. So everybody, I hope you saw important things, whatever things change, but draw the things separately, and that's what you do for any pulley. It's a walk in the park. It's nonsense. Here they told us that, and by the way, for this one it was like in the Y. Here it was like in the X for here, because this is, we are dealing with this, and this is the only force acting in the X. So since it's the only one, we know that the resultant should give us MA, because it's not balanced. It's not balanced. So that's the situation, and that's what we did, and we put the result, and we put the forces that are giving us the result, and we make them equal to MA, and we solve. Why is it like I can't see myself yet on the YouTube thing? So anyway, we go on. Right. Pinky pinky punky for the donkey. Let's quickly talk about this one. How you do, but they didn't say anything to do with 2D. And I mean, Finding missing forces, no. They didn't say anything to do with that. So anyway, the maximum height, this type of questions, no. I'm going to leave that one. There's a chance it's not coming. We start with the things that we know are coming. We try to do as many questions as we can. Boom, 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 boom. Increase your chances of getting it correct. So let's go. Here's another one. What is it saying? Hey, cut, blah, blah, blah. When you get a system, when you get a question on momentum, you draw these diagrams. If they're drawn for you already, use them. Okay? You draw these diagrams. If they're drawn for you already, nice. Before collision, after collision. We call them the system diagrams. Okay? For momentum, the secret is that we do not care what happens. There are a lot of questions I'm going to show you again, by the way, on forces. We just need to do a lot of questions on forces. And I'm not going to do the whole thing, but I'll be showing you an important part that I need you to remember, even from your tutorials, because one of them is coming. One of them is coming. So we're going to have to do that and do it and do it and do it and do it. And just remember and just do graphs and graphs and graphs. So for momentum, what is it that you gotta know? You should remember that we don't care what happens during the collision. We want to know before. Just before they collided. And after they collided, what was happening? That's what we care about. So in here we are saying, okay, here is the before collision. You write what was happening. Don't show us what was happening during collision. We don't care about that. So here they showed you, okay, just before the collision, this was happening. Then after the collision was finished, this is what was now happening. Yes, we're going to do questions in all the tests that you want. In the test, yes, we should revise questions in the test. I agree with you, 100%, because he said you should. So here we have this. So what is the total momentum in the combined cuts after the collision? Momentum after the collision. Here after the collision, they are joined together, so they move together, so we are going to count it as one. And what you do is you add the masses. This is 2 kg and 3 kg, so the mass of this new guy is going to be, this is the mass of the 2 and the 3 kgs, which means the total mass is going to be the 5 kg thing. So we have a 5 kg thing, and we have the velocity of 2 and 3, the final one. This is going to be the same. And that velocity, here did they tell us the velocity? After which both are moving at this. So don't read too much of the question, you will lose marks. Read important parts and answer the question. So quick. So what you'd be saying, what is the total momentum of the combined cuts after the collision? You're going to say momentum of object 2, 3, because one was 2 kgs, the other one was 3 kgs, so we can call them objects 2 and 3. Momentum is going to be equal to momentum of this. You can say it is good mass of the 2 plus mass of the 3, multiplying the velocity of 2, 3, the final one. Okay? Which you can put it like this. Then now you're going to say momentum of 2, 3, the momentum of object, since it's stuck, it's called object 2, 3. So we're going to say momentum of object 2, 3 in x is going to be mass of 2 plus mass of 3 plus, or multiplying, velocity of 2, 3 in final, or in x, the final one. We do the velocity in x. Once you say in x, you don't put these arrows here. So what is that going to be? Momentum, 5 kgs, 5.00 kgs, multiplying the velocity that they are moving at. What is that velocity? They told us. They said they are moving at a velocity of 3 meters per second. So you're going to say multiply by 3.0 meters per second. What are we going to get? Momentum is, this is the idea. You should always look. Don't try to read the question too much. If you read the question too much, it is going to cost you. You hear me? Let me check if you guys can see me. Okay, good. Don't read the question too much. Do the important parts. So it's going to be 5 times 3, and you're going to get 15 kilogram, 15.0 to 3SF, or to 3 kilogram dot meters per second. This is what we have. Okay. You could have made it a 15 strictly because of these two SF. So it's 15. There we go. This is going to be the final one. we're done. It's just mass times velocity. It was too cheap. The questions that actually come in tests and exams are way, way, way too easy. Okay, let's go to the next question. What is the total kinetic energy? Kinetic energy of the combined cuts. So it's the same thing. You're going to say kinetic energy of object 2, 3. This is going to be, what do you know about kinetic energy? It's half mv squared. So it's half m1 plus m2. Okay, it's m2 plus m3 because they're combined mass. Then v23 squared. Half mv squared is going to be the kinetic energy, which is going to be half the mass of the two, 5.00 kgs, times their velocity of 2 and 3. They say they live at the velocity of 3.0 meters per second. Then you're going to get the kinetic energy. It's just half mv squared. And because it's stuck, it's one thing. You put the mass as just one thing. And because they are stuck, they have the same velocity. You just put that velocity. You put in the calculator, you're going to get 3 squared is 9 times 5, 45. So it'll be 45 over 2 and whatever. Okay. Then calculate the impulse, the thing reject. So impulse is equal to force times time. Or we say the impulse is going to be the change in momentum. So we're going to say the impulse is going to be the change in momentum. That's the other word for impulse, change in momentum. So 3 kg cut. So you're going to say impulse is going to be delta mv, which is going to be change in momentum. Okay, change in momentum, which is going to be now, what happens? You're going to say, to get that, it's going to be m times delta v. Here you're dealing with the 3 kg cut, so it's m3 by delta v3. It will be the velocity, okay? So this is going to be our impulse. It is delta mv. Which is going to be m. Then we're going to say the velocity. So here it will be these two. You subtract the final minus the initial, which is 0. We all know that the initial is 0 because we saw that. This becomes m3 times velocity of 3 in x, the final one, which is going to be the mass of the third thing is going to be 3 kg cut times the velocity, which is the final velocity. So it's going to be here, calculate the during, so it's going to be m, which is 3 kgs, times, here we have v3 in x, the final. So what is this going to be equal to? 3 kgs times, here you put it. So what is the velocity in the x, the final? So in here, let's go and take that final velocity. Okay, so here, that's 3 kg cut. The final velocity is the velocity that they moved away with together. And it was 3 meters per second. And the initial one was 0. That is why. So you're going to say 3 kg times 3.0 meters per second. 9 kilogram meters per second. Okay. Simple fixture. What type of collision took place? And please tell us now. Now, the reason you're going to, it's going to be a perfectly inelastic. Perfectly inelastic collision. Why is it a perfectly inelastic collision? It's a perfectly inelastic because object gets stuck. And because objects because the object get because object got stuck okay. So here, if they get stuck together after collision, that collision will now be called perfectly inelastic. And that is what we did here, and that is what should be done. You're done with this one. You move on. Okay, this type of question will come back to it, but we're not interested. Anyway, we've seen these questions, and they are the typical questions that come forward. Let's look for another paper. Right, here's another one, which you must do. Person holding whatever. Of course, you draw the free body diagram of the bow. We are not interested in you, Mr. Person. Whatever it is, we don't care. We need to show the forces acting. That's the only thing you gotta put. Surely you can. Then, whatever. I mean, it's show or assumptions. But this question is not asking for things we are interested in. So, we are leaving him. We want to resolve for forces. Here, calculate acceleration. These are the types of questions we want. Here's another the box sitting on the thing. We can put a free body diagram for this guy. Free body diagram. We can put it. It's just going to be, we put your dot. Then you show that, okay. So in here we have that rope. So you have this, and then you have its weight. Then you have its normal force, which is going to be the same size as the weight. Something like this. Make sure the biggest forces get the longest arrows. So anyway, so what we'll be saying is the tension blah 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 is this. They told me in the x direction as a result of the, if the coefficient of friction is this, calculate the magnitude of the friction force. Oh, there is friction, so there is something which is going to be acting like this, and it's going to be small. It's called the force of friction. Here is going to be the weight, which is equal to the weight. Actually, we were told it's 2.50 times 1.50. So what are we going to get? Find the value of the weight. What is the weight? It is equal to the mass. 1.5 times 9.80. So yeah, we put this. There we have. What is the answer? Let me punch. 14.7 newtons. You just draw the free body diagram. Force in a rope is called tension. This is the normal force. Force of friction or X in the opposite. So here's our free body. This is easy. Hey, coefficient, what? Let me tell you what you need to know now. You need to know that the force of friction, when you're getting it, it's mu, then you multiply by the normal force. You can say by this or by n, it's still fine. It's mu, which is by n. Or this is the force of friction. Then you're going to have the force on a spring. Let's say you are compressing a spring, or you are extending it. The force you are putting on the spring, you always get it by saying K delta X. But if we want the force that the spring puts on bodies, we don't like that one. We don't like springs that fight back, but they always do. And the force that springs do is going to be negative K delta X. This is the force by a spring. In other words, if that's the Fs, if you are putting the forces a certain thing went through, then you put negative K delta X if it is something that was being pushed by a spring. So in here we have this for friction. The force of friction is mu n. Then the force of this is 900. So let's go. So is mu n the normal force? So now we would say, what is the normal force? For this case, the normal force is equal and opposite to the gym. So you'd say, okay, the normal force is equal to the N, which is equal to 14.7 newtons. So here we have our normal force, and we're going to say the force of friction is equal to mu N, mu K times N, which is going to be equal to, that mu is what? So here you get 0.136. So this is now, we are now saying the force of friction is equal to mu N, which is equal to 0.136 by here. So N will be by 14.7 newtons, which you multiply and you should get an answer. 0.136 times, this is 14, man. It's a walk in the park. 1.9992 newtons. So now what are we going to do? They said calculate the magnitude of the friction force. Oh, we got it. Calculate the acceleration of the object A in X. A in X, acceleration in the X. Yes. So how do we get the acceleration in the X? Summation of forces in the X. This should give me, are they equal to 0? No! So this should give me, they should be equal to mass times acceleration in the X. So now let's add the forces in the X. We put them here. Tension is right. Force of friction is left. So it's going to be the tension minus the force of friction. This should give us mass times acceleration in x. So we say, okay, what is the tension? What is the tension? Hello? What is the tension? Have we been given tension? Let's find out. Have we been given tension? The tension is 2.50 newtons. Yes, we have been given tension. So you are going to say 2.50 newtons minus force of friction. There we go, 1.992. 1.9992 newtons. This is equal to mass. What is the mass of this object? Do we know? Yes, we know. Somewhere. Where is its mass? 1.50 kgs. So we're going to say it is going to be equal to 1.50 kgs by A in x. We don't know that A in x. That 1.5 goes to the other side. 2.50 newtons minus 1.9992 newtons divided by 1.50 kgs. This will be equal to A in x. You put in the calculator, you get your A in x. Ding, ding. So you're going to say, okay, 2.50 minus 1.9992 is equal to, you say divided by 1.50 is equal to, you're going to get 0.33 whatever. Here we'll put to 2SF or to 3SF, 0.333. This is going to be what? Newtons, or we can say meters per second squared. This is going to be our acceleration in x. So everything is on free body diagram, yes. So on free body diagram, I ignore everything else, yes. I just look at the forces acting, yes. If it's a pull, yes. If it's a whatever, come on. Here's a free body diagram. You've done the calculation. Something like this is coming tomorrow. Hey, you know. After some time, the object moved the distance. So this is delta x. Calculate the work done by the friction force over this distance. So work done, we can talk about work done by each force. Each force does its own work. And work is just what? Work done is equal to force times delta x, which is going to be the work done is the force of, in here we're saying the work done by friction is equal to the force of friction by delta x. We want to find work done by delta. Okay, but now let's talk about this. We know that this is how to get the work done by the force of friction. But we have been told that after some time, here, after some time, the object moved this distance. Calculate the work done by the friction force on the object over this distance. Work done by the friction force on the object over this distance. So it moved a distance of what? 0.257. What was it that was acting on this thing? If you look, these type of questions, which is this body, you may get it. I know that it is not. I know that it is not part of the questions that he mentioned, but you may just get it to complete the thing, because this would be your chapter 9 type questions. I wanted to see if I could look for them and show you. This would be your chapter 9 type questions where you're saying, okay, I don't know if anyone has ever gone through chapter 9. It's the very same topic or questions as other chapters, only that one of the questions you're asked is for friction. So, yes, we're going to say, calculate the work done by the friction force on the object over this distance. We'll be saying, like I said, let me just give me 1 second to show you so that I can just confirm and show you what I want to show you. Work done by only one force, and we have a situation with many forces. Where is the tutorial? I wanted to look for it and show you, but I'm not finding it. It doesn't matter. It doesn't matter. But if you want the work done by each force, you'll be just multiplying each force by this distance that was going to be moved. So it's fine. You just say friction by that distance. Now you'd say, what is my friction? Did we find it? 1.9992. So 1.9992 by their distance 0. So times delta x, they said after some time it moves a distance of what? 0.250. So you are going to multiply this in newtons by 0.250 meters. That's your work. Then you're going to get the work that was done. Okay? Now, this is work done by the force of friction. Then you are done. Well done. Let's go to the next question, if there is one. Choose the term that would best fit the missing word in order to make the most general statement. Work performed by a resultant force in the dash of an object's body. Work performed by a resultant force results in the dash of an object's energy. Increase, decrease, or change. Work performed by a resultant force. Okay? Work that is being performed by a resultant force. What does it cause a change in? Does it cause a change in your energy? Does it cause a decrease in your energy? Or does it cause an increase? All the time. If we say increase, it means all the time it will be an increase. When you do what? When you do work by a resultant force. Will it always be? Will work always be an increase? Can you have a decrease in work? Okay, can you decrease the work done if work is being done by a resultant? Or here, will there be a change of the object's energy? Well, it's easy. When you perform work on a body, you are giving it energy. If I carry a box, I am giving it energy. Work is the way of transferring energy from one object to another. So, resultant force does what? Work. That's what matters. It does work. And what does it cause? Increase in energy. Because we are giving it energy by working on it. So that guy who said change, ridiculous. It can never be decreased. It is always increased. I can't see you guys. Let me check if you're there. Hey, blah, blah, blah. Hey, this is the thing. These are the questions we want, man. Because a question with something like this, a spring, can cause an acceleration. We've seen how pulleys can cause acceleration. Ropes can cause acceleration. You just need to draw the free body diagram. And it's a dot. Don't draw the bus there. Hey. If you do it in the exam, what a risk taker you would be. Because you surely will be punished. Do you hear me? Right. Look at this one. Here we have a track or whatever it is. Do we care? No. Free body diagram, please. Time for the free body diagram. And let me give you a tip. Usually they'll tell you when the spring is now pushing back. So here they're saying, draw a free body diagram of all forces acting on the cut. Free body diagram, they'll tell you of who. Here they said of the cut. Thank you. The moment the spring is released. So when you release the spring, stay awake, push, push, push. When you release the spring, it's now pushing the cut. It is now pushing the cut. So basically we have this force, which is like this, and we say force by the spring. Then we're going to have what else? What other force is acting on the cut? Is the cut pushing in? Hell no. It is just being pushed away by this spring. Then what else do we have? We just have the weight. And we also have the normal, which is exactly the same size as the weight. This, if you want, you can make this force smaller, just to show that they can have different lengths, but whatever. Now here we talk about draw free body diagram. We have done 3 marks for those 3. Then we do part B. Give the force as well as its reaction pair that caused the acceleration of the cut. Give the force that caused the acceleration of the cut. This is force by the spring on the cut. Okay? And then you'd be saying, what about its reaction? Its reaction would now be, what about its reaction? The reaction would now be force by the cut on the spring. Action reaction, simple fixture, we move on. Now, if the spring constant is this, how much was the spring compressed? So we are looking here. Spring. Is the spring a vertical force? Hell no. The spring is a what? Horizontal force. The spring is a horizontal. So what are we going to say? The summation of the forces in the X is equal to MA. Now what are we going to say? What are the forces acting in the X? Only the force, what? The force by the spring on the cut. And what is it? We say summation of forces. Since it's facing the left, it's negative Fs. This is going to be equal to MA in X. Now what are we going to say? What are we going to say here? We're going to say, what is our force, this force here? Remember, okay, when we are doing resultant, we first just put it as it is. When we are doing the resultant, we first just put it, we always add these things. But now when we are putting here, we would say, okay, I want the force, this is not the force on the spring, it's force by a spring. So it will be negative K delta X. And this will be equal to MA in X. Isn't it? Here we want to find out the change. They said, by how much was the spring compressed? We must get a negative value for delta X. And here, and they say the spring constant is this. Compressed the moment that it was released to accelerate. Here, let's go and find that acceleration. The spring is released with an acceleration of 0.5 what. Now remember that here this was negative because this force was facing the left. And now we know that it will be also a negative K delta X because this is a force by the spring. So this Fs is the negative K delta X. Then this negative quantity is the one which then goes here. So now what are we going to say now? We are going to find the delta X. We say negative, it's now K delta X is equal to MA in X. Now we are going to say delta X is equal to MA in X over K. There we go. Which means that the delta X, the compression, which should come out as negative if we are correct, is going to be, what is the mass? 0.725 kgs. So 0.725 kgs. By the acceleration, what is the acceleration? Negative 0.515 meters per second. Negative, because its acceleration is to the left. Remember, this thing is going to the left. So negative 0.515 meters per second squared. Divided by K. What is the value of K? Here, 12.5 newtons per meter. So divided by 12.5 newtons per meter. You are going to get your delta X. And that is going to be the compression. What is that delta X going to be? Just the sum of forces in the X is equal to MA in X because they are talking about compression of the spring. So it is depending on that. Come on. And you get your 3 marks. Do you see that? Put the calculation, please. Somebody. Put the calculation. 0.725 minus 0.515 divided by 12.5. We'll actually get a positive value. Wow, that's crazy. What is the answer going to be? Check what the answer is going to be. Meaning, I think this is a message to us that when we are doing resultant, we should always add forces. Because it's true, in resultant, forces are always added, like in here, in resultant. So maybe this one was always supposed to be added because we are dealing with resultant forces. Resultant, you always add. Don't know, the sign will take care of itself. So in here, that is when you're supposed to put negative, because this is why. Why did we put negative? Because this is force by the spring. We don't like the force by the spring. Remember, we are dealing with the forces on the cut, which means it is by the spring. And the force by the spring is negative. So that means this was going to be what? I would have taken this, it would have been a negative K. Okay, because it would have been a negative K delta. You'd have a negative K, so you'd have a negative, because you should get your delta X being negative. Then you know you are correct. Correct, correct, correct. What is that delta X? You put it in there, you get your thing. That's the game. Draw the free body diagram, Captain. Draw the free. If it is momentum, draw the two system diagrams. And if they want you to find initial momentum there or momentum wherever, draw the system diagrams. You'll be fine. You will be fine. If you draw the system diagrams, then you're going to be fine. For here, draw the free body diagram and do summation of forces in the X is MA in X. They will never be zero. Because they already told you now that the situation you're doing in the exam is for when there will be a resultant. So wake up. It's not like the book, which was sitting and balanced. No. You get your answer, delta X, and you can now say your compression will be. For compression, you don't have to put the negative because you've already said compression. Now you can put your whatever meters, how much the spring was compressed. You feel me? Give me more. Let's send me on my WhatsApp. Oh, somebody. Send me on my WhatsApp the test 1 and test 2. Send me on my WhatsApp the test 1 and test 2s. Somebody. Send me on my WhatsApp, and we also need to talk about the graphs. Send me, somebody, the test 1 and test 2s. CK, CP, send me the thing. Okay, I'm gonna go live again. Let me crop the papers. Let me look for the test one and test two and crop them, right? And I'm because I'm using the same device which I'm using to do live. Then I'll send another link. Just wait. We'll call this part one. Then we'll do part two and part three. We'll do the questions, more questions, and I want to take screenshots of like questions from the tutorials that ask about this stuff we've been doing of free body diagram, summation of forces is equal to ma in x, and graphs and multiple choice. We'll be just doing till you guys are tired. Those who sleep can sleep and whatever.